Hi all, good evening. I hope you can hear me. My name is Shovik De and we are going to look at assignment 12 of the course Power System Analysis. Of course, as we know, assignment 12 is of the previous run and these problems will help you in solving the current assignment problems. So this is the last assignment and after this session is over I will be recording my uploading this session on YouTube, and I will also be mentioning my email ID over there so that if there is any doubt you can mail me so that I can clarify your doubts in the future. So let's start now. I'll be sharing my screen shortly. I hope my screen is visible. So let's start. Yeah. So assignment 12 will be based on the synchronous stabilities, the steady state and the transient state stabilities, the swing equations of the synchronous generators. So this is one of the most important topics of power system analysis, and you can expect a lot of questions from here. Uh, and it is equally as important as assignment 11, the uh, fault related problems which we saw last week. So we will be discussing some typical questions for this assignment 12, and at the end also I have given another problem which is of course not present in this assignment questions, but it is a very common question which you can expect in the exam. So having said this, let's start. So question number 1, two power stations A and B are located close together. Station A has four identical generator sets, each rated 100 MVA and each having an inertia constant of 9 megajoule per MVA. So this becomes our H as we know. Whereas station B has three sets, means three generators, each rated at 200 MVA and having an inertia constant of 4 megajoule per MVA. So the question is, calculate the inertia constant in megajoule per MVA of the equivalent machines of both the stations on a base of 150 MVA. So let's start. So as we know, this HA, that is of power station A, the inertia constant of all the four generators. So we had a identical four generator sets. So they are having an inertia constant of 9 megajoule per MVA, and the rating of each generator is 100 MVA. Similarly, for station B, it is HB is 4 megajoule per MVA, and there are three such generators. So we have to calculate the kinetic energy, the total kinetic energy of station A, which means the multiplication of the inertia constant as well as the rating of the generator and multiplied by the total number of generators. So basically 4 into 9 into 100, which is your 3600 megajoule. Similarly, for station B, we get 2400 megajoule. Now the total system, so total means the total kinetic energy of station A and B is your this 3600 plus 2400, that is of station A and B. It comes out to be 6000 megajoule. Now the base rating is 150 MVA. Therefore, the equivalent inertia constant of this total system on this base would be simple. this would be 6000 divided by 150, which comes out to be 40 megajoule per MVA, which is your option number C. So pretty simple problem to start with. I hope it is clear. So let's now go to question number 3. Um, Here it is said that an alternator is connected to an infinite bus as shown is in this figure. It delivers a power of, it delivers 1 per unit current at 0.8 power factor lagging at a voltage. The magnitude of the voltage is 1 per unit. So this is the voltage of this bus, infinite bus. Now the reactance of this alternator is 1.06 per unit, and now they have said that keeping the active power fixed, if the excitation is reduced, find the critical excitation voltage in per unit corresponding to the operation at steady state limit. So we have to find out what would be the value of this alternator voltage or the excitation voltage at steady state limit. So steady state limit basically means, so we know this formula of the active power for a generator which is connected to an infinite bus. So here we are neglecting the resistance, so that is why we only have the single term. Otherwise you have two terms here, as you know. So now at steady state limit, we know that this load, this power angle, this delta value, it is 90 degree. So this comes out, so this becomes 1 and we are left out with this. So now replacing all the terms here, so it comes out to be 0.85 per unit. Okay. So okay, no, sorry. Now basically we have to first calculate what is the value of this steady state power, right? So because finally we have to calculate what is the value of this E, that is the excitation voltage. Now here if you see in this formula, if you see, we have two unknowns, right? We don't know this, and as well as we don't know this. So we have to first calculate what is the value of this steady state power. Now for this we know we have been given the current as well as the voltage, right, at the infinite bus. So the current is 1 at an angle of minus 31.79. This is because the power factor is given, which is 0.85 lagging, as well as the bus voltage is given, which is 1 per unit. Now having known these three informations, it is we can calculate what is the value of this steady state power, which is 0.85 per unit. Now we know this. Now having we can replace this value in this formula, and we get the value, the magnitude of the excitation voltage, which is your 0.901 per unit, which is your option number C. So pretty simple problem, because we had been told that this was operating at steady state power. So this made the whole problem pretty simple. As well as we were given with all the details of the infinite bus. So pretty simple problem. I hope this was clear. Now let's go to question number 4. So I keep on checking the recording is going on, because previously I did face a lot of issues. And it's a problem of MS Teams that sometimes, due to some reason or the other, maybe due to internet problem or something, the recording stops. So we have to do it all over again. Yeah, sorry for that. So let's discuss question number 4. So an alternator is connected to an infinite bus as shown in this figure. It delivers, so it is basically the same problem. 3 and 4 are connected problem. So it delivers 1 per unit current at this power factor lagging, where the bus voltage is this much. The reactance of the alternator is also given. And now keeping the power factor, the active part fixed, the excitation is reduced such that the steady state limit of the operation is reached. Now they are telling find the reactive power supplied to the grid at this operating point. So at this operating point means at steady state limit. So steady state basically means your this delta, the load angle, this must be 90 degree. So this is the formula of the reactive power provided if we neglect the resistance, right? Because this is a purely inductive line, as you see in this figure number 4. So now replacing this delta equals to 90, this whole term becomes 0 and we are left with this. So when we replace all the values, we get 0.9434 with a negative sign. Now Q with a negative sign means that it is delivering this reactive, this power, right? Reactive power. That is why this becomes leading. So your option is A. So now let's go to question number 5. Um, Here they have mentioned key in a single machine infinite bus system where the machine is directly connected to the infinite bus with a reactance. The maximum steady state power transfer capability is 1.5 per unit, right? So this becomes your maximum power which the uh, synchronous machine can deliver, which is your 1.5 per unit. So the machine delivers X per unit active power to the infinite bus. Now the value of synchronizing power coefficient of the machine at this situation is found to be zero point 0.9 per unit. So what is the value of X, or the this active power which is being delivered? So we are being given with this information, as I told, this P max, or the maximum steady state power which can be transferred, it is 1.5 per unit. Now the this X is the power which is being transferred to the infinite bus. Now the synchronizing power coefficient is your del P del, right, which is your zero point 0.9 per unit. Now we know this expression X is equal to P max into sine delta. Now when we differentiate this, we get this cos delta term, right, which is your zero point 0.9. Now you know this P max, which is your 1.5, and hence your del comes out to be 53.13 degrees. Now when you replace this into this, and also you know this, it comes out to be 1.2 per unit, which is your X. So this is what we were told to find out, right? So this becomes your option number C. Pretty simple problem. So
What does it mean, this synchronizing power coefficient?
this has a significance. So this is related to the stability of the synchronous machine. So basically dp d del, basically it represents the slope of your p power angle curve, right? So from minus 90 to 90 degrees, your if you plot the curve, if you know what is going on, so basically what would be this curve? This would be a sinusoidal curve, right? Starting from 0 degree, from 0 to it goes from to maximum at 90, and then it becomes 0 at 180. So when you take the differentiation of this, it is maximum at 0, and it is 0 at 90 and 0 at minus 90, right? So this becomes your this thing, the slope. So basically you have to operate the system where your slope is positive, where the point when your slope becomes negative, so below 9 yeah, so when your slope becomes negative, so then it means that it is losing its synchronism, basically. So this is the significance of this synchronizing power coefficient.
Okay, if it is operating in negative zone means a small amount of instability would result in out of sync, right?
Yeah,
Okay.
yeah. Okay, so now let's go to question number 6. So at 200 MVA, 11 kV, 3-phase, 60 Hertz, 8-pole synchronous generator, a lot of informations are given. Has an inertia constant H equal to 2.25 kilojoule per kVA. Now the stored energy in the rotor of the generator at synchronous speed will be, so so basically they are asking to find out what is the kinetic energy stored in the machine, right? So if you know the formula, it is kinetic energy is equal to half I into omega square, where your I is moment of inertia and omega is your this thing, um, angular velocity. It is in mechanical radian per second, not the electrical value, right? Because you're considering a mechanical system, the rotor is rotating, right? The shaft is rotating, and it is equal to, that is equal to G, which is the machine rating, and your inertia constant H. So it doesn't depend upon, so as you can see, it doesn't depend upon the synchronous speed. So you don't have to get confused using by looking at this term. So basically you have to multiply 200 into 2.25. uh, yeah, so which is your option number, so it comes out to be 450 megajoule. And also yeah, this would be down here. So I was actually moving these, while writing I was actually moving these terms here and there, so accidentally it got up. So anyways, I'll correct it and then resend it. So what I want to say is that, see, your H, the unit is kilojoule per kVA, right? And both the numerator and denominator has kVA. So easily you can replace it. I mean, write it as megajoule per MV. It doesn't make any change. Hence, you can multiply this and it comes out to be 450 megajoule, which is your option number D. So I hope it was clear. Pretty simple problem. Now let us go to question number 9, the more complex problems actually. So yeah, so these problems tend to be more lengthy because of the informations that are given there. So as you can see, there are a lot of information. So these consume the spaces actually. So figure 9 shows the single line diagram of a single machine infinite bus system where the generator is connected to the infinite bus with a transformer and a double circuit line. So this is the transformer and this is the double circuit line. Now the inertia constant is this much, frequency is this, mechanical power to the prime mover, which is your PM, right? So this is the mechanical power which you are giving, and the system is operating at stable equilibrium point within the rotor angle equal to 30 degrees. So your del 0, this becomes 30 degree. So this del 0 here, this is equal to 30 degree electrical. Now the infinite bus is maintained at 1 per unit voltage. So the voltage at this point, right, it is 1 per unit, and the internal voltage of the generator is kept constant at 1.2 per unit. So basically you can say this at this point the voltage is 1.2 per unit, and it is known that the synchronous reactance of the generator is 0.35 per unit, and the leakage reactance of the transformer is 0.25 per unit. So basically I have drawn it here. So this, you have the reactance of the this generator and as well as the transformer. So this is 0.35 and this is 0.25. And yeah, for schedule maintenance, one of the lines, that is one of this line, right? Because there are two transmission lines operating in parallel. So one of the lines is switched off. So they are asking find the new rotor angle at the new stable equilibrium point to transmit the same amount of power. So I mean this PM would be same, right? So that is why they are telling you to transmit the same amount of power from the generator to infinite bus if all the other parameters are kept unchanged. So I hope the question was clear. Lot of informations were given here. Mm, yeah, okay. So now this is the diagram, very simple diagram. So this is This is the generator, this is the transformer, and these are the two transmission lines. So one thing you will see here, we don't know what is the value of, what is the impedance value of these transmission lines, right, in per unit. So that we have to find out. So for that, I mean, we know this equation, right? PM is equal to Vg into Vb, the magnitude of them divided by the equivalent inductance into sine delta 0. So we replace all of these and we get the value to be 1 per unit. Now this is equal to, so these are all connected in series and this is in parallel, so that is why divided by 2. And from this you can calculate what is the value of XTL, right? It comes out to be 0.8 per unit. Now they are telling key for schedule maintenance, one of the lines is switched off. So your new network becomes this, right? And now they are telling what would be the load angle, right? Considering the same amount of power from the generator to the infinite bus. So you have to now calculate what is the new inductance value of the line. So this becomes your, so this plus this, it becomes 1.4 per unit. And again your equation remains the same, only thing is that this changes and this changes, everything all other remains the same. So we know everything, we just calculated what is the new inductance of the line, right? So this comes out to be, the load angle comes out to be 44.427 degrees, which is your option number C. So I hope
Okay.
this problem was clear.
Yeah. So which means that when I'm operating at lesser lines, I mean, if I'm increasing the number of lines, my stability point would be lesser for the same load, or
Hmm.
I'll be more stable. When the lines are getting reduced, then
Yeah.
I'll move on to unstable zone or
Yes.
increased delta zone. Okay.
Yeah. Basically, your inductance is increasing now for
Okay.
this line.
Okay. Okay.
So that is hampering your stability point of operation.
Okay.
Yeah. Uh, Now this is problem number 11. So this is also pretty, I mean, related with this critical angle problem. So I hope you know what is critical angle, right? So
And one more question. Sorry to interrupt. One
yeah,
more
yeah, yeah,
question. In that case, in the in previous question itself, so
yeah.
whenever I switch on a breaker, a line, I'm taking line into service or I'm taking out of service,
Hmm.
there is a change in delta. So which means that there will be some kind of oscillation happening
Mm-hmm. Yes, yes,
during that
yes,
time, right?
yes,
Okay.
yes, yes, yes.
Okay. Okay.
I mean, during
Okay.
that time, your damper windings placed in the rotor of the synchronous generator will start operating, right? It will damp out the oscillations and it will, I mean, settle at the new equilibrium point.
Okay, okay. Because I never thought about this thing. I only considered it in the view of load alone. For 600 megawatt, okay, I'm going to have two lines, which is going to have total 600 megawatt. And if I'm going to have one load also or one line also, that is going to deliver the 600 megawatt.
Yeah, this is
That
a
was my
common
idea.
phenomenon, right? Because
Yeah,
see,
yes.
in case of so if you have a this thing, so for example, you have a fault at the middle point, right? Then I mean, we will be looking into this problem. We have a problem. Then all of a sudden, your line impedance changes and it
Yeah.
affects the stability, right? It's a
Okay.
transient.
Okay.
Yeah.
Yes, okay, okay. Yeah, it's clear. Thanks.
Okay. So now question number 11. So a generator operating at 50 hertz delivers 1 per unit power to an infinite bus through a purely resistive network. So I haven't drawn the diagram here. It's pretty simple. So not much components are there. So that is why I didn't draw. Anyway, so the maximum power that could be delivered by the generator is 2 per unit, right? So this is Pmax, your Pmax. Now a three-phase fault occurs at the terminal of the generator at t equals to 0, which reduces the generator output to 0. So this is very important. The generator, so during the fault, your generator output becomes 0. So the fault is now cleared at time t equals to tc. So critical time. This becomes your tc, critical time. Now the original network is thereafter restored. So the maximum swing of the angle is found to be delta max equals to 110 degrees. So if the inertia constant is 4 per unit, determine this critical time. So basically fault clearing time. So, I mean, if you look into the literature, this is the formula for the critical clearing time, where this, you know, all of these terms, right? So, only your this PA is the acceleration power, which is your PM minus PE at the time of fault, right? So, at the time of fault, clearly they have told that the generated output is reduced to zero. Therefore, your PE is zero. So, your acceleration power becomes PM. Now, we have to calculate what is this critical angle, right? So hence, I mean, now let's proceed to calculate that. So okay, so for that we first calculate what is this delta zero. So this is very simple. So sine inverse p0 by p max. So the mechanical power initially before fault was 1 per unit and the maximum power was 2, right? So this becomes sine inverse 1 by 2, which is 30 degrees. Okay, so one thing here, so this Pmax and PM both are same, huh? So don't, okay, so I did a mistake. I'll correct this. So this would be Pmax, not PM. So don't just confuse this with this. So this will be Pmax. Here also in this formula also this will be Pmax. I'll just correct it while uploading. So this is your critical angle, right? So the load angle at which the breakers operate, right? So this is this delta C, or critical angle. So I mean there is a detailed derivation using uh, this equal angle criterion if you see the textbooks. So this is the formula. Now, as you can see, this will be Pmax. So Pmax into R1. So this R1 is nothing but a numerical coefficient. So this is during fault, and this Pmax into R2 is after the fault is cleared. Now, if you see, clearly they are telling ki this is I mean generated output during the fault is reduced to zero, right? So this, therefore you can say this whole thing will be equal to zero. Therefore, I mean your R1 is zero, right? So, I mean, as a result, if you see this formula here, this term will be equal to zero. So, we are left with only this term, right? And I mean, from every term, your Pmax will get cancelled. And now, therefore, your R1 is zero, and what will be R2? So, clearly, they have told that after the fault is clear, the original network is restored, right? So, therefore, your generator is again delivering a power of 1 per unit. So therefore your R2 will be your 1. So now, I mean, you can replace, I mean, substitute every values you know here. So you know del M, del 0, everything you know. And this will be in radians, okay? So you have to multiply pi by 180 degrees. So when you do this, it comes out to be 0.356 and your del Z comes out to be 69.138 degrees. So now you replace this all the values here in this critical clearing time. It comes out to be 0.1865 seconds. So again, this also will be in radians, huh? This won't be in degrees. So I hope this problem was clear. Question number
Yeah,
11.
yes.
Okay. We'll be looking at another problem. So another problem, this would be a more much complex problem. Okay, so question number 12 now. This is a pretty simple problem compared to question number 11. A 50 hertz synchronous generator is connected to an infinite bus through a line. The per unit reactance of the generator and the line are your zero point 0.3 and zero point 0.2 per unit. Now the bus voltage, okay, the generator no load voltage is maintained at 1.1 per unit and your infinite bus voltage is maintained at 1 per unit. So the inertia constant is 3 megajoule per MVA. So they are asking key determine the frequency of natural oscillation if the generator is loaded to 0.6 or 60% of its maximum power transfer capability, and the system is subjected to small perturbation in power. So okay, so for frequency, oscillations, we have to use this formula here. Now they have told key the generator is loaded to 60% of its maximum power transfer capability. So your delta zero or initial load angle comes out to be 36.87 degrees. Now also you calculate the P max, you know every value here, so it comes out to be 2.2 per unit. Now, okay, so you need this synchronizing power coefficient, right? Del PM, del del. So you calculate this. So 2.2 into cos of 36.87. So it comes out to be 1.76 per unit. Now this AM, as we know, so this will be in radians, right? Not in electrical degrees. So otherwise this would have been, instead of pi, this would have been 180. So, and we have replaced G with 1 per unit because we are considering everything in base value here. So that is why this is 1. So now you replace everything, it comes out to be 1. So yeah, it is in radian per second, this frequency ka unit. So this comes out to be 9.6 radian per second. To convert it in hertz, as we know, we have to divide it by 2 pi, so this comes out to be 1.528. So just be very careful while you are solving these problems. There would be, you have to be careful with radians and degrees and also the units, especially of this frequency oscillation and also of this critical clearing time. So we get 1.528 hertz, which is your option number B. I hope this was clear. Okay. So now we go to one problem. So this is not in the assignment. This is, I thought of including. So this is a problem which I found in one of the textbooks which I normally use for power system analysis. I have used in my BTech. So this is a pretty interesting problem. Yeah. So let's go through it. So figure below shows a generator connected to this infinite bus through high voltage lines. Now you see these are all breakers, These are all breakers. So breakers adjacent to a fault on both sides are arranged to clear simultaneously. Determine the critical clearing angle for the generator for a three-phase fault at a point P. So fault is occurring here where the generator is delivering 1 per unit power. So your P0 becomes 1 per unit. Now assume that the voltage behind the transient reactance is 1 per unit. So your this thing is 1.2 per unit for the generator, and the voltage at the infinite bus is your 1 per unit. So having said this, we have to calculate what is the critical clearing angle. Now clearly you can see for this type of system, during when the fault is occurring here, during the fault there will be a power transfer through this line, right? So in question number 11 we clearly saw this line that the generator output is reducing to 0, but in question number 13 this won't be the case, right? Because there is a path for current to flow through this line, right? So the output won't be 0 during the fault. So we have three cases. Before the fault we have to calculate what is the power during the fault and after the fault. So using that we have to calculate what is the critical clearing angle. So now let's proceed. So initially we will look at what is before fault. So as we know, our mechanical power input is 1 per unit, and we have to calculate what is the equivalent reactance of this whole system. So this is before the fault. Now pretty simple. So this is the transformer. This is the line. Again, this is the transformer. Same for the line below it. and we get an equivalent reactance of 0.725 per unit. Now using this information we calculate what is the value of delta 0, right? So it is 37.17 per unit, and also your P max, this thing comes out to be 1.655 per unit. So this is pretty simple. Now let's come to what happens during fault. So 1 minute. Yeah, Lakshmi, you can hear me, right?
Yes.
Okay. So during fault, as we can see that the fault occurs at this point, right? At point P. So just after the transmission line, right? At this sorry, just after the transformer, just before the transmission line. So at this point. So just I have tried to simplify it. So this is 0.55 and this is 0.15 and this is zero point 0.4. Now you can see that this network is basically a delta network, right? Like if I arrange it, because this is ground, right? So if you try to join these 2 points, this point and this point, you will see that this is a delta network. So we basically have to simplify this network for calculating your this equivalent reactance of this line during the fault. So for this, I mean, you can clearly see that this is a delta network. Now what we try to do, we try to convert into star. So delta to star transformation for this and this. Now we do this, we convert this into star. So this becomes my equivalent network. Now clearly you can see this becomes in series and this becomes in series. Now this is the equivalent networks. Again what we do, we try to convert this into this thing delta, because this is a star network. So what we do, we try to convert into delta network. So basically the start to delta value of this and this is 3.133 per unit, and we are not interested in the impedance or the reactance value of these lines, because my power will basically flow from here to here. So hence my equivalent reactance becomes 3.133 per unit, and my power P max during fault becomes 3.83 per unit. So I hope this was clear. So after this I'll come to after fault, but I hope till this point this whole thing was clear to you.
Yes.
Okay. So after fault is very simple. You, I mean, basically we remove this line, right? So the breaker, due to this, this breaker will operate and this whole line will get removed. So we are left with this upper line. This line we are left with. So our equivalent reactance after fault AF becomes 1 per unit and my Pmax becomes 1.2. Now again that same formula, and as we saw in question number 11 that it was clearly mentioned that your power during fault reduces to 0, but for this case it is not. I mean, we do have a power flow during the fault, hence this term, the R1 which we saw, this won't be 0 here, and we have to calculate each of these terms here. So hence we go on calculating. So P max during fault is your R1 into P max. Okay. So P max is basically the value before fault. So when the line was operating normally. So we calculated this, right? P max during fault came out to be your 0.383, and therefore your R1 becomes 0.231. And this is P max after fault. This also we calculated 1.2. So this becomes 0.725 per unit. So now we have to calculate what this delta M value, right? So basically your what is the rotor swing, right? So this is, so as you know, I mean we write it as this. So sine theta is equal to sine 180 minus theta, right? So hence our delta M comes out to be 123.56. And now we try to substitute every we know each and every term, right? We know what is delta 0, delta M, P max, everything we know. And anyways, your Pmax, everything get cancelled. We know R2, R1, everything we know. And we finally get what is the critical clearing angle, which is your 48.687 degrees. So this was the whole problem. It was a pretty lengthy problem, but yes, it is a very common phenomenon in power system, and you can expect some problem, this kind of problem in exam. I hope this was clear.
Yeah. Yes.
Okay. So lastly, so this is the last problem, pretty simple problem. So a 4-pole 50 hertz 22 kV turbo alternator has this rating 100 MVA 0.8 power factor lagging. The moment of inertia or I is 8,000 kg meter square. Determine the inertia constant H. Now, as we know that as we saw a problem, right? Initially, that we were told to probably in question number 1. So kinetic energy we had to find out. So this was equal to G into H. So again, kinetic energy is also equal to half into I into omega square. So be careful. I mean, this is omega electrical. Huh? This angular velocity is the electrical angular velocity. But I mean, since this is a rotor and this is a, I mean, mechanical part, so we have to consider the mechanical angular velocity for this kind of problem. So we have to convert W into Wm, and we know that We, I mean, angular velocity is P by 2 into your omega m, right? Where P is the number of poles of the rotating machine, right? So we have been told that P is equal to 4, therefore we can calculate what is Wm. And now we just substitute this, and your H comes out to be 0.987 megajoule per MVA, which is your option number A. So this was problem number 2. I hope this was also clear.
Yes.
Okay. So yeah, this was assignment number 12, and this is your last assignment for this course. So yeah, I'll be uploading this today by today only, and I'll be making the necessary corrections in this PDF file. Okay.
I have a few questions.
Yeah, yeah,
If
yeah.
you can stop the recording, then I'll
Yeah,
forward.
one minute. 1 minute. Yeah.